All right, welcome everyone to example 1 of chapter 3. In this problem, we're trying to determine some unknown vector E, both the magnitude and direction. All right, so what you see here on the left are two displacements for two different cyclists biking from some common starting point, and they both want to reach some campground, right, up here. Overall, right, their average displacement, right, or their overall resultant goes from their start point to their end point as vector C, right? But they take two different paths. Cyclist 1 takes vector A, right, to the right, and then turns, we'll say, up along the vector B to reach the campground. Cyclist 2 starts from the start point and goes straight up for a long ways on vector D, and then takes some unknown vector E to reach the campground. Right? It's our goal to find both the magnitude and direction. Okay? So, first off, we need to write down some general vector statement that describes this scenario. Okay? It says that C is the resultant for both. So that means if we add up the vectors in both paths, that should equal C. So for 1, we have A plus B, right? Only in vector form. And that's also equal to vectors D plus E. Okay? I'm just keeping this all positive and still in vector form for right now. Okay? We don't immediately know numbers for C. We do know for A, B, and D. So since we're trying to find everything we can about vector E, let's just keep it in terms of A, B, and D. All right? What I mean is, let's solve this statement for E. Right? And so this is what we have now, right? Purely in vector form, this will give us a guide or a template, right? Or a starting point, if you will, as to how to solve for the x and y components of E and then ultimately E itself. Okay? Because we do know numbers for A, B, and D, right? The problem tells us that. So this is the statement here. This is the vector statement that will break up into x and y. Okay? And what I mean is we ultimately want to find something like this. The x component of E, right, times I hat, plus the y component of E in the j hat, right? We want to find numbers for both of those. Well, you can do that by using this vector sentence or vector statement that we found earlier and just doing it purely in x and purely in y. So let's see here. I want to do that. Let me do that. Okay. I'll just keep it in magnitude form for right now. Let's see how that goes, right? So the magnitude of EX, well, that's AX plus BX minus DX, okay? And then, well, I'll skip a line and do EY. EY is the same thing, but in Y. So A plus B minus D, all right? Okay, and now it's time to plug in some numbers. So AX, right here, do we have that number? Yes, we do. The x component of vector A is completely in the x direction. I just realized, right? I keep saying x and y, but really, this picture here does not specify x and y, right? So I was kind of shorting you by accident, right? we need to specify ourselves before we do any math the x and y directions. Okay? And so just simply writing it down beside the picture is more than enough. Okay? This way, if you do this on your problem, say for an exam, I will know what you're basing your numbers on. Okay? I will know how you get your numbers. Okay? So now we can see that this AX term right there is that one. And so in other words, A is the same as AX. And so that equals 1,080. I'm going to leave meters off. No, I'm not. I'll leave it in there. BX, does that cancel out? What's that value? Well, it's the x component of vector B. Vector B, it says, is completely now in the plus y direction. There is no x component. So that's 0. Is there an x component for vector D? Also, no. D is purely in plus y. And so this magnitude is 1080, just like the classic Nintendo snowboarding game 1080 Snowboarding, right? Look it up. It'll date me. I don't care. All right, y direction. The y component for vector A, well, we just said that it's only an x, so that's 0. The y component for vector B, that is the 1430 right here, right? It's completely in the y direction, so plus 1430 meters. And now subtract the y component for vector D. So keep in mind here, this minus sign has to remain there because this came from our algebra when we derived this statement originally. Okay? So even though the magnitude is positive, 1950, yeah, okay. Even though the magnitude of D, or dy in this case, is positive 1950, that negative sign has to stay there. Okay? And so this leads to a magnitude for EY of minus 520 meters. Okay? So we have a magnitude for both, and we can find the overall resultant for EY, right? I believe we can. So I'm going to skip to the next slide because I'm running out of room quickly. So let's see. The magnitude of vector E is simply EX squared plus EY squared square root. And we just found those numbers. So that was 1080 plus negative 520. Okay, here again, that plus is coming from the Pythagorean theorem itself. The magnitude of EY includes the negative. Okay, so don't simply put that negative out there, right? That's not what happens. You have to include the negative when you input the magnitude for EY, and then quantity square that. So if you do that, you should get roughly an overall magnitude of 1,200 meters for vector E. Okay. So before we get our angle, let's quickly sketch this as a triangle here. Let's see what happens. Okay, going back and seeing what vector E should look like, right? In general, it goes down and to the right. So I'm going to draw something like that. Let's see. Let's see something like, nope. Nope. Maybe. Let's do that. Let's stick with it. So if I say that's vector E, the x component if you look closely, is about twice in magnitude what the y component is. So that's what I tried to draw here, right? The x component, I'll draw it in blue, EX, is roughly twice the length of the y component, EY. So hopefully we can see that a little bit. And so now we are free to choose the angle, right? To determine the angle from whichever point we choose, okay? Let's choose this angle here, because then we can reference from the x-axis, okay? So to find the angle, since now we know both x and y components, right, both sides, a and b in other words, we can do inverse tangent of opposite over adjacent. Right? And so this is inverse tangent of, what was EY? Negative 520. Again, keep that minus sign in there. That's part of that magnitude over the x component of 1080. And this should be approximately, where's my notes? Negative 25.7 degrees. Okay. So, negative 25.7, and that should make sense, right? If it was 45, that would mean that both x and y magnitudes were equal. So because x is twice as much as y, the angle is about half of 45, so 25, close, okay? So that's in the ballpark at least. If you were to use, say, this angle here, right, let's do it for phi. Let's say you chose that position. Well, inverse tangent of phi, tangent is still opposite over adjacent. Okay. What does this come out to be? So inverse tangent now of 1080 over negative 520. If you do this calculation, I bet you'll get the, what is that, the component? So it's equal to 90 minus 25.7, which is 64.3. Okay, so whichever angle you specify, you have to specify where it's measured from. This minus sign, by convention, means that the angle is going clockwise, right? That 64.3, that can be, let's see, that's kind of a weird spot to do it, because remember in the diagram here, the cyclist was starting at this location and going this way, right? So the 67.3, I guess, would be this angle here. So this would be the phi there. So then you would say from that direction, so that would be a positive 64.3, and you could even say from the minus y hat direction, if you wanted to, right? Again, at least in this problem, I would stick with this convention, right? That location for the angle, in that case, inverse tangent of negative 520 over 1080, and it's about negative 25.7, okay? So, thanks for watching this video. There we go. And stay tuned for example 2, where we have more practice with vectors. All right, thanks for watching.